Hello. In this video, we are going to be looking at inverse functions. And so let me start with something that might provoke your imagination. It's called the dating rule. You might have heard of it. So you should only date someone half your age plus 7 or more. It's been said that. Actually, this was come up with by someone in 1901, and it's been used in several occasions. And I think it was on a TV show, either Friends or The Big Bang Theory. So you should only date somebody half your age plus 7 or more. So for me, that would mean that the lowest age of a person I could date would be somebody like Taylor Swift, like that. Later on in this video, we'll find out, like, if you're younger, how old you would need to sort of cut off your dating. So how old of a person you could date. So let's talk about inverses first, and we'll get back to that question. If we let R be a relation, then the inverse of R is denoted as R inverse. So R to the -1. So R inverse, and that's the set of all ordered pairs BA, such that you have an ordered pair AB and R. So in other words, what we're going to do with an inverse relationship is we're going to switch the order of X and Y. And that's exactly what happens here. So the first and second coordinate of each are exchanged, and thus the domain and range of the relations in an inverse relation are also exchanged. Let's look at an example of this with just 3 discrete points. We have a relation given by 3 discrete points. We want to find the inverse and the domain and range of the relation and its inverse. So the inverse is easy enough to find. We denote it by R to the -1, and we just go ahead and swap those coordinates. So the point -1, 4, the point 2, -3, and the point 5, 0 make up that inverse relationship. If I was trying to find the domain and the range of the original function and the inverse, the domain of the original function would just be the x values of that original function. So 4, -3, and 0. That should be the same as the range of the inverse function. So remember, the range are the y values, and with my inverse function, my y values are 4, -3, and 0. What's the range of the original function? It's the y values of the original function, -1, 2, and 5. That should be the same as the domain of that inverse function. And there they are, -1, 2, and 5. So hopefully that gives you a little bit of insight to a function and its inverse, how things are really just swapped. Okay, so the inverse of f of x will only be a function if every pair of distinct elements in x1 and x2 in the domain of f, their y values don't equal each other. Now, this is very mathematical. We won't be using this definition too much because we'll try to leverage the graphs. A more useful way to say this, if you were to be actually doing it mathematically, would be to say if f of x sub 1 is equal to f of x sub 2. So really what that says is if we have 2 y values that are equal in the range of f, then they came from the same x value in the domain. Again, we can do this a lot easier graphically. So graphically, we have this thing called the horizontal line test. Remember, the vertical line test was there to help us with determining whether a relation was a function. The horizontal line test, furthermore, verifies if that function is going to be 1-to-1, which would mean it's invertible. So graphically, the horizontal line test states that if a function is 1-to-1, so this is a little terminology. So 1-to-1 would mean that it's going to be invertible. So an inverse would exist if and only if no horizontal line intersects the graph more than once. Let's take a look at some examples of this. So here we have a graph. This looks like a cubic function. It could be a y to the fifth. But if I was to draw any horizontal line along this graph, it would only cross the graph once. Now it's sort of hard to see here at the middle, but it's true. So this one is 1-to-1. Yes. 1-to-1 because it passes the horizontal line test. What about a linear function? We have a linear function. As long as these linear functions have some slope, they're going to pass the horizontal line test. This one, notice, has a y-intercept of 0, 5, 1, 2, 3, 4, 5, and it's decreasing. So our slope is -2/1. I go down 2, and I go over 1, and I can draw that line. So if I can graph the function, I can tell if it's going to be 1-to-1 or not. And of course, any line you draw is going to be strictly increasing or decreasing as long as it has some slope. So all these lines are going to pass the horizontal line test. So yes, it's going to be 1-to-1. And this is just a shorthand way of saying 1-to-1 because it passes the vertical line test. Okay, now let's look at an absolute value graph. We know what this looks like. It looks like a line with +1 slope to the right and a line with -1 slope to the left of the y-axis. So you can see that there is one point where I can draw a horizontal line through and it crosses in one place, but there are many, many more, and there has to be at least one. So here is one where I draw the line through the graph and it crosses more than once. So this one is not 1-to-1 because it doesn't pass that horizontal line test. And this, I see right now, I wrote vertical line test. That's for a function, right? So this should be horizontal line test. My apologies. So we're drawing horizontal lines here. What I want to sort of impress on you is we can illustrate the definition this way, the alternate definition. So notice if we have this absolute value function, let's say that we have the point 2, 2 over here, and the point -2, 2 up here. So we have 2, 2, and -2, 2. Notice in this case, f of x1 is equal to f of x2. So both these points have 2 for their output value in the range. So if it's 1-to-1, they're supposed to come from the same x value. But notice that this one came from -2 and 2. So it came from 2 different x values. These weren't equal. So that's a way to algebraically show that this is not 1-to-1. So you would have f of 2 is equal to f of -2. However, x equals 2 is not equal to x equals -2, of course. So they came from 2 different x values in the domain. Another way to sort of show that this one doesn't have an inverse. All right. So now that we sort of identified these, which ones have inverses and don't, 1-to-1 functions are important because they are the ones that possess inverses. So these first two would have an inverse, and we could find it. The last one does not. It turns out if f is a 1-to-1 function with domain A and range B, the inverse function, which is denoted f to the -1 of x, has domain B and range A. So just like above, where the X and Y coordinates are swapped, the domain and range is swapped, and we saw that up above. One thing to realize is that when we're dealing with functions, f to the -1 is the notation for an inverse. It does not mean 1 over f. So you have to be a little careful there. If you do go on to take trigonometry, or if you've taken trigonometry before, you've actually seen cases where you deal with inverse functions. And we will later too, when we deal with exponentials and logs. So it turns out that when you have an inverse function, if you can find it, it has a nice property because it undoes the original function. So if f is a one-to-one function with domain A and range B, the inverse function satisfies the following cancellation properties. So we go back to our composition. If I compose f inverse in f and apply that to any x value, I will always get that x value back. It's like division, it's like dividing by a function, but it does it with functions that can't be divided. So this is actually going to go ahead and undo that function. Similarly, if I have an inverse function and if I apply the function to an inverse function, I will get back what's in the middle there, what it's applied to. So this is going to be a great rule to help us, especially when we deal with those functions that we need to find the inverses of. So in the second part of this video, I'm going to answer the question, and we'll see how we actually find those inverses. Okay, I'm back. What we're going to do first before I show you how to find the inverse is we're actually going to be looking at how we would see if we had inverses, how we would show that they are inverses of each other. So we're going to make use of the rule where when we compose functions, we get x's back. So in both cases, A and B here, we have functions that are inverses of each other. Again, we don't know how we found them, but they're there. So to show that these are inverses, we are going to take f and compose it with g. We remember how to do that. The first thing I taught you to do was to rewrite it as f of g of x. We plug in that function x minus 2 for g of x, and then we go back to our f function, and wherever we see an input, we're going to put that x minus 2 in. So I'm going to have 2 from the f function, and then I'm going to put this input in, x over 2. So when I take 2 times x over 2, so the 2 cancels, and I get x back, as we would expect. If I do g of x, I should get the same thing. So g of f of x would mean that I have g of f of x, or g with the 2x in there, that's my f of x. So now I go to my g function, and wherever I see x, I'm going to plug in this 2x. I get 2x over 2, and again, the 2's cancel, and I get x back there. Let's try one more here. I'm going to do the same thing over here. So f of g of x, I write that as f of g of x. I plug in my g of x, which is 3 minus 4x. And then I go to my f function here, and wherever I see an x, I'm going to plug in this 3 minus 4x. So I'll have 3 minus 4x all over 4. I distribute the negative, so I have 3 minus 3 plus 4x over 4. Notice that 3 minus 3 is 0, and 4x over 4 does give me x. So that one checks out. If I compose them the other way, I should still get x. Let's give it a try. So g of f of x is equal to g of, here's my f of x, 3x minus x over 4. I go to my g function, I plug in 3 minus x over 4, wherever I see an x here. So that's what I plug in for my input. I'll get 3 minus 4 times 3 minus x over 4. The 4's will cancel. And I'll get 3, distribute the negative, minus 3, minus a minus x is plus x, which would give me 3 minus 3 plus x. And that checks out. So whenever I compose a function with its inverse, I always get those two sort of undo each other. And I get that creamy center back. So whenever I compose a function with its inverse, we'll always get that creamy center back. I want to show you one more thing here, which is sort of neat. For instance, with this first set of functions, if I were to plot these, so you might see the 2x and the x minus 2, there's some graphical sense to what's going on here. It turns out that when we plot these, maybe I wanted to make this color pop a little bit more, but it's hard to do with this calculator. So I'm going to make this blurry for a minute, and then it will come back. There we go. You might be able to see that this first graph here is going to be the one with the slope that's less dramatic, the 1/2 slope. So this is g of x is equal to x over 2. That's actually in red. And in blue, I have the slope of 2. F of x is equal to 2x. Notice that these are both symmetric with a certain line, and that line is going to be y is equal to x. So if I plot that black line going through there, these graphs of functions and inverses will always be symmetric to that line y is equal to x. And that should sort of make sense, because if I do have a point x comma y on the first graph, then the point y comma x will be on the second graph. So it'll just sort of reflect around this line y is equal to x. Here at 0, 0, all of these are the same. Okay, I wanted to show you that because I just thought it was a cool result. Let me show you how to find inverses now. So it's sort of a cookbook way to do things, but that's nice because there's a rule we can just follow for every example. So to find the formula for an inverse, f inverse of a one-to-one function, so first of all, it has to be one-to-one. What we're going to do is we're going to first start by replacing that function by the variable y. So if I'm looking at finding the inverse of this function, the first thing I'm going to do is replace that f of x by y. The next thing I'm going to do is switch x and y around, because really that's what an inverse does, right? It switches x and y. So I'm going to put x in for y and y in for x. The next thing I'm going to do is solve the new equation for y. So this is a line. To do that, I would subtract 3. That's my third step. I divide by a -5. But notice I really don't like negatives in the denominator, so I'm going to distribute this -5 up and make this a -x plus 3 over 5, or, well, I'll just do that, -x plus 3 over 5. So I've solved for y, and then finally, I replace that y variable with the symbol of an inverse. So the inverse of that function 3 minus 5x above is -x plus 3 over 5. There it is. And finally, what I could do is I could take f of g of x and show that that's equal to g of f of x, which is equal to x. So we could do what we did up top. Not totally necessary if you're confident in what you did, but it is a good check. Let's try to do this one. So first step, replace f of x by y. Second step, I switch x and y around. So x is equal to y minus 1 cubed plus 2. Now I'm going to solve for y. If you sort of look at the function, maybe you can get a sense of why we're doing what we do. So what this function does is it's going to take the input, subtract 1, cube it, and then add 2 at the end. So if we were doing the total reverse of that, what we would do is we would start by subtracting 2. That was the last step we did here, so it's the first step we do here. So subtract 2. And then we cube the function. So to get rid of the cube, we take the cube root. That would be the next step. And finally, remember, we subtracted 1 from the function at first, so we add 1 from this function at the end. So that might give you more of a sense of why this works. So there's my function, and I can replace it by, if I want to, I can just put f inverse at first, so I can replace that y by f inverse. So f inverse is the cube root of x minus 2 plus 1. So what this function does is it subtracts 2 first, it takes the cube root of that, and then it adds 1. So it does all the reverse steps here in the exact reverse order. All right, of course you could do your check if you wanted to at the end. Finally, before we get back to the first question, we can use inverse functions with discrete points. So if I know that I have a function that's 1 to 1, so it has an inverse, if I have f of 5 is equal to negative 22, then I should be able to find f inverse of an input of negative 22. So remember, these two just switch with inverses, so my output should be 5. Okay, so let's go back to this question that I was posing to you. So the dating rule, you should only date someone half your age plus 7 or more. So I could actually make a function out of this, but let's sort of take this into your hands. So let's say that you're 20 years old. And by this rule, what is the oldest person you could date? All right. So like in my case, I'm an old guy, so I would take my age, blah, 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 and divide it by 2 and get blah, 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 and add 7, and I would find the youngest person I could date. Now you're 20, so what we're going to do is we're going to take the reverse of this rule. So the first thing I did was half my age, and then I added 7. So the first thing you should do is subtract 7 from your age, and you would get 13. And then what I did was half my age, so I'm going to double this age. And so it turns out if you're 20 years old, you should probably, by this rule, only be dating somebody that's going to be 26 years old max. Now, I don't totally believe that, but we could use inverses to sort of do this. If you wanted to look at it mathematically, you could do that. So my dating functions, I'm going to call this the dating function, d of x is equal that I'll take my age, divide by 2, and add 7. So if you wanted to find your age, what you would do is, first of all, replace d of x by y. I would switch the values of x and y around. And then we'll go ahead and solve for y. So I would subtract 7, just like we did here. I would multiply by 2, just like we did here. So y would be your inverse, or in this case, we would call it d inverse. So a younger person would subtract 7 from their age and then double it. And that would be the oldest person that they would want to date according to this rule. All right. I hope this has helped. Thanks.